Yeah, we start with Unit 1, Nature of Physical Laws. As stated here, physics is concerned with the study of matter and energy in transit. The theoretical structure is as follows. Now, there are four types of physics. The first and the foremost is classical physics. As stated here, before the 20th century, scientists understood these things. Matter is composed of particles and obeys Newton's laws of motion. Second one is radiant energy is composed of waves and obeys Maxwell's electromagnetic field theory. Till to date, this type is extremely successful. But when particle speed is compared to speed of light, that is 3 into 10 to the power 8 meters per second, and second one is particle size is of the order of 10 to the power minus 10 meters or less, this classical physics theory fails. Now when it fails, there comes two theories to handle these two problems. Now one is the particle speed is compared to the speed of light, that is being tackled by the theory of relativity by Einstein, and particle size is the order of 10 to the minus 10 meters or less, handled by the quantum mechanics. Now what is theory of relativity what is the theory of relativity? When particle speed rises to nearly the speed of light, Newton's laws are no longer obeyed. Theory of relativity. When particle speed is compared to speed of light, Newton's laws are not obeyed. But theory of relativity can successfully explain this failure. Third one is quantum mechanics, quantum physics or quantum mechanics. The second failure part, that is the particle size is of the order of 10 to the minus 10 meter or less, is handled by quantum mechanics. We will be coming to know about this theory from Heisenberg, Schrödinger, also de Broglie, Dirac. These are the people or the scientists behind this quantum mechanics theory. Now, in contradiction to the classical concept, it establishes the dual nature of both matter and radiation. That means it is a dual nature of matter and radiation. The last one is quantum field theory. Now this encompasses both the theories of relativity and quantum mechanics. Therefore, if this field theory encompasses the theories of both relativity and quantum mechanics, then they can describe the behaviors of very high speed microscopic particles. It describes the behaviors of very high speed microscopic particles. Now we come to the concept of conservation principles. Now, a few inherent symmetries of nature led the physicists to accept some conservation principles, out of which the four are very important. Conservation of mass energy is the first one. In classical physics, it was known as the conservation of energy. Einstein, after he discovered the E is equal to mc square part, he converted this into conservation of mass and energy principle. Second one is conservation of linear momentum. Conservation of linear momentum. And the third is the conservation of angular momentum. And the fourth is conservation of charge. All these conservation principles will be studied in the chapters to come. Now we come to the four basic interactions. Out of these four interactions, only four types of interactions among matter and energy are essential in nature. They exist in nature. The first one is gravitational interaction. Now, gravitational interaction, we all know, is of attractive nature. It is an attraction between two masses. Between two masses, its range is infinite, but practically it may not be detectable beyond a large but finite distance. Second one is electromagnetic interaction. Electromagnetic interaction. Now, this interaction is both attractive and repulsive. The second point, we can say that if it is electrostatic attraction or repulsion, that is it between two charges, and that between two magnetic poles, we call it as a magnetic. So between two charges and between two magnetic poles, the range is similar to that of the gravitational interaction. Range similar to gravitational. And after this comes the strong or nuclear attractions. Very strong or nuclear interaction. It is the attraction between protons and neutrons, as you know. Attraction, protons and neutron attraction. Second point is that the range is of the order of, it's a very short range force. Range is very short, or the order of 10 to the power minus 14 meters. Beyond this range, the interaction force becomes zero. The last one is weak interaction. Why do we find this weak interaction? Between an outermost electron with a proton or a neutron within nuclear dimensions. It is attraction. Attraction. Attraction is not will not be the correct word. Interaction between electron with a proton or a neutron. Its range is also very short. Its range is also very short. Range is very short, and this force ceases beyond 10 to the power minus 15 meters. The ratio of the strengths of these four interactions, a ratio of these four interactions according to order, 1 is to 10 to the power 37 is to 10 to the power 39 is to 10 to the power 27. Now from this ratio we understand that gravitational interaction is the weakest and the nuclear interaction is the strongest. Gravitational interaction is the weakest and nuclear interaction is the strongest. So this is the weakest and this is the strongest.